Okay, so I'm very happy to welcome Kapil, who's from Roku, who's going to talk about improving search relevance using cross-encoders and LLMs. Over to you.
Yeah, thanks, Charlie. So LLMs are a great tool in general to improve search relevance, but they have two key limitations. One is latency, another is cost. I'm sure a lot of you have faced those. So what we did and what I'm going to walk you through is one of the use cases where we started with LLMs and then we replaced them with a much smaller model. I'll share my learnings that we had. So first of all, what is Roku? It's not really popular in UK, so I wanted to make sure people know what it is. So we are a streaming platform. We have our own TVs, streaming sticks. About the scale, it's more than 50% of the households who have internet in US have a Roku TV or Roku device. Around 125 million users. We use Roku to stream movies, shows every day. When you turn on the TV, it looks something like this. You have apps. You go to Netflix, any app that you like, or there is a recommended topics for you. And then when we go to search, we have search homepage, which shows search history and what could be potentially you could be searching next and other stuff. And then obviously there is a search bar. You can do a text search, a voice search. You can directly look for Moana, or you can say a girl on a voyage. So queries could be anything, and we need to bring the right content for the user. So agenda-wise, I'll briefly talk about the search at Roku infrastructure, like stack-wise, not tech stack, but we'll see what it is. And then semantic search, bi-encoder models, LLMs as a judge, then go to cross-encoders, and finally some results and some ongoing work. This is not an exhaustive list, but I just wanted to clear out the architecture that we have. For query understanding, we have, obviously, we do intent classification. We try to understand this query. User is looking for a sports, movies. What is he looking for? Some NER is done, and some query expansion. There is a debate in the company what we should call a query expansion or not. For example, what we do is when a user looks for Harry Potter, we bring in not only Harry Potter, but a row of, let's say, magical fantasy and the realm around that movie. Retrieval-wise, we have kept lexical retrieval. We'll talk about it while we kept it. We use Elasticsearch. Then we have semantic retrieval, bi-encoder models, and most recently, we have delved into generative retrieval, essentially for latest items. Then we have a merging layer. We experimented with various ways of doing it. RL, from RL to basic interleaving. I should say the other way around, from interleaving to RL. Then we have ranking. It takes care of all the personalization, but we do have a flavor of personalization in retrieval as well, but more heavy lifting stuff is done in the ranking layer. Short-term interest, users long-term interest, heavy models. When I say heavy models, it's transformers. It's generative recommenders, DLRM. We've had an evolution of these. And after that, we do re-ranking, which is essentially trying to balance the engagement and monetization, because some of the queries could be exploratory in nature. User could say action movies, and it's up to us what movies we show or what content we show. It could be behind a paywall, or it could be free for this user. Then some business rules. We have to respect certain contracts we have with different providers like Netflix or YouTube, and then some layer of diversity and freshness. Yeah, I think previous talk sort of was based on this. So I'll not spend much time, but essentially, how do we do semantic searches? We embed all the documents, and then when a query comes, we try to find the closest documents and return those documents. So how do we do it? We essentially use a bi-encoder model, which is we embed all the items, index them. Then when the query comes in real time, we generate the embedding. It could be cached as well, but we embed it, find it. So how was it helpful at Roku? We were able to do queries like show me funny movies, which are sort of synonyms. We're able to do character plot-based queries, movies with strong female leads, TV series adapted from comic books. It is very fast for us. We use Onyx plus some GPU optimizations we do. I would say around 30 to 40 milliseconds is the latency. Then what are the cons? It brings long tail items, as we catch up from the previous talk. It doesn't have a sense of popularity. If a user is doing a query action movies, it could bring action movies from which are not really popular and didn't do well. We can build a separate index for that and sort of leave that to the merging layer to fix. But we have tried other approaches, which I'll talk about in the next slide. The other con could be the cold start does not have. So essentially, when we don't support semantic search, we don't have those queries with us. So we can't really train the model. So we have to synthetically generate that training data. We use LLMs to do that. And then quality of embedding, we also realize degrades as the text grows. So let's say we went to LLM and tell and Wikipedia and all the other sources about a movie or a series. We collected all that data. Now the text has become big. And we've seen that quality of embedding degrades. We have tried chunking and other different ways to fix that. Essentially, embedding is not able to capture all the semantic meaning after a certain length. Obviously, there's a token limit as well. And if we use the default version, we don't have much personalization. So what do we do? On the left, you see we started off with the bi-encoders, which we had pre-trained encoders. And then there's a thing missing in the slide, which was using the synthetic data to improve those, fine-tune those encoders. And then once we have those, we bring it into our personalized training of bi-encoders, which is sort of fine-tuned personalized encoders, which is where we give the user's history sequence as one of the inputs and other features, essentially the user and the query context. And on the right side, we have the item metadata, item ID, and other item-related features. Now, when we do that, it's still not able to solve few problems. And there was a question that what to do with these false positives that come. So essentially what happens is, let's say if there is a query mystery involving cats. Now, the model could bring this other item, which is amazing animals. It's about cats, but it's not really a mystery about cats, which is a very hard sort of, it's slightly relevant to the query. It's not completely relevant, but they do happen even after a lot of fine tuning of those bi-encoder models, even trying to bring in good quality negatives, hard negatives, and whatnot. So how do we deal with this? We said, let's see if LLMs can do this for us. Essentially what we do is we get the results from the bi-encoder layer, get the movies and series, let's say top 100, and then we send each one of them to the LLM along with the items metadata and ask LLM, hey, do you think it's relevant to this query or not? Now, the problem with this is, yeah, of course, it can handle hard negatives. So the problem is the latency. Of course, it'll take 1 to 2 seconds if you're using the proprietary LLMs. Even if you host, the latency could be around 200, 200 milliseconds, even for a very small LLM, even if you fine tune it. And then, of course, the computational costs are high. It cannot handle. So for each query the user does, I'm trying to call this LLM, let's say 100 times, which is not cost effective. So there comes cross-encoders. And what we do is, so again, the architecture overall is same. The movies and the items come from the bi-encoder layer. They go into the cross-encoder. Cross-encoder gives us a score. We'll look into a minute what cross-encoder is. And then based on that threshold, we decide whether to send it to the ranker or not. It was cost effective. Essentially, it's like a 4 million parameter model compared to an LLM. So it's much cheaper to run. Now, what is a cross-encoder? So essentially in bi-encoder, when we train them, you saw that the query side and the item side are sort of independent. There is no interaction till the last layer where we can compute the similarity score. With cross-encoder, now the BERT has an access to both the query and the item details. So it's able to effectively make a decision. Now, these cross-encoders also vary. They could be as big as, I think, 24, or even we can add more layers, attention layers. So even it's not cost effective to run the default, let's say 24 layer attention, cross-encoder. So what we did was some explanations. So let's say So CrossEncoders is able to access both the query and the document tokens. When we tried it out, we sort of visualized one of the attention layers, what it is doing. So it's able to sort of try to understand the semantic meaning across the query and the document tokens. That's why it's able to understand and give a relevant score. There is a paper which talks about that it's sort of a BM25, but semantic in nature. It's able to understand the semantic meaning. If there is a word which is semantically relevant to the query, it does give a high score. Now, what we did was we used a very small version, like the smallest cross-encoder, which is TinyBird, which based on TinyBird, which has 2 attention layers. And to evaluate how it is doing, we used LLMs. We got 10,000 pairs judged by the LLM if a query item pair is relevant or not. Pass it on to the TinyBird and let it evaluate it. When we evaluated it, you could see that it was not able to do a good job by default because there could be many reasons for this. One is it has only 2 attention layers. Initial layers just focus on the sort of keywords overlap. It's not really doing much semantic. The other reason is the pre-trained models don't understand the domain of movies and series. So what we did was we said, okay, we're going to fine tune it. Again, we had these examples from the LLMs. We fine tuned a TinyBird model. On the left side, you see before fine tuning and after fine tuning, it's able to separate the labels between relevant and irrelevant. We sort of, once we did that, we saw, of course, the improvement in precision recall, but also we released it to the users and we saw a drop in abandonment rate and visit to stream. Now, what are the next steps we are doing? We realized that cross-encoders, then one of the main differences between cross-encoders and the LLM is, for this task, is LLMs also have some inherent knowledge. So even if your metadata quality is not good, it can understand what that movie is about, whether it's relevant to a query or not. But here we need to do metadata. So the model, the item description has to contain that data, which we are trying to match to the query. So some better metadata hydration. We also want to integrate human labels because LLMs are also not like 100% correct. So we have some internal results where we realize that accuracy is not 100%. So we are trying to integrate those. We're trying to add more features to the cross-encoder, which is BM25 score, some more query and item past interactions. We also want to do is experiment with something where after the retrieval layer, we have just one model, which does the personalization and the cross-encoder bit both into one, or somehow parallelize those paths because they are sequential at this moment, which slows things down. Yeah, thank you.
Thank you very much. So, does anyone have any questions for Kapil? Yes.
Thanks very much. That was a great talk. With the kind of judgment data, you said you're using LLMs. Do you have quite a simple method for doing that? Like, do you have complex prompts to do that? Because it's something that we're looking at doing as well. And we're trying to weigh up the, I guess, the complexity of the LLM labeling and then how you judge that against human labeled stuff. And that seems to be one of our biggest troubles, is getting that kind of ground truth data correct.
Yeah, so what we do is we use an ensemble of LLMs. It's not just one LLM. So you generally have an odd number of LLM to decide. That has helped. Prompts help, but again, what has helped us more is trying to understand the things which are popular on web, how it is doing on those compared to things which are not popular on web, and adding more additional information to the LLM.
So using implicit feedback alongside the LLMs to sort of guide the accuracy measurements?
Not till now. We are now integrating that. But let's say if you have to generate this data set, so it depends on the domain, right? So our domain, if a new movie is released and LLM does not have the information about that when it was trained, it does not do a great job. Even the LLMs which have a search, so now they are able to search as well. Like they have a search tool integration. even then they're not great at new stuff. So yeah.
Thank you.
Hi, thanks for the talk. So when you do this teacher fine-tuning of the tiny BERT cross-encoder, what teacher model do you use?
It's the LLMs.
Oh, LLMs. Okay, so trying to make it as good as LLMs. So from your experience, how far it reaches like in performance when you use LLMs as a teacher? Like what is the difference between the metrics for the tiny BERT and the LLM? Oh,
Yeah,
okay.
so we are not still 100%. We are able to achieve a precision of 89 and recall of 81. Oh, sorry, recall of 81.
Okay.
The gap here is because of the metadata quality. So cross-encoders do not have the inherent knowledge. So you have to provide that information about the items. That's one reason. Second, having a little more, because when I say, when I quote this 81 or 89% precision, it's assuming LLM is doing correctly
Correct,
100% of the time. So we need some human labeling as well.
Okay.
And then, yeah.
Cool. Thank you.
Any other questions for Kapil? Yes.
Hi, how do you account for recency and rise in popularity of something that your model may not have accounted for at training time?
Yeah, recency for this is generally depends on how recent we're talking about. So if generally these movies have Wikipedia pages and other information when they're released, especially if there is a good movie coming up, generally has a lot of information. So we have pipelines that automatically pull that information. We have a whole system that does that. What was the other part of the question?
Rise in popularity.
Rise in popularity, we as search are able to track it really fast because people generally come to search and search for that movie. So we get very early feedback on that.
Okay. So it's dependent on explicit user interaction.
Yeah, but for this model, popularity doesn't is not as big a factor because here what we're trying to do is reduce the false positives after the bi-encoder layer. Popularity plays an important role at the first layer where we have the bi-encoder models. And to deal with the popularity there, like something fresh has coming, we don't have just one retrieval source. We always have the lexical match to cover it up. So if someone searches for a very new thing and its dual encoder model is still not trained, we have that to cover at that gap. And the second is to deliver high quality items to the user. Let's say if something new has come up, we have realized that a lot of models the models we had previously have a lot of gaps in recommending the new items. So we have generative retrieval to take care of that part.
Okay, another one, sorry. How about monetization of, again, recency? A new product, a new film comes out and basically want to use your platform as a way to advertise themselves. How does that affect the rest of the inventory and the...
So it depends on, sorry. It depends on what that agreement with that provider is. So sometimes they could specifically come to us to promote that. So it will vary. It may not go even through this whole setup. It may be a dedicated row. It depends on the contract with that provider in those scenarios, if they really want us to highlight something. That's why in the stack, we have in the end some business rules that we need to cater for.
It's funny how you can build a perfect search engine, but there's always the commercial imperative as well. Any other questions?
Hi, I'm not familiar with the movies data set, but I wonder if you tried, for example, using Wikipedia categories and subcategories to understand, build a knowledge graph of your movies. For example, the mystery movies involving cats. would be under subcategory of mystery, will be under subcategory of movies involving cats. And this data, which is available just open source, or at least an open data set. So rather than matching between your query and the movie, you match between query and categories and subcategories. And from there, you can match on movies, because I imagine movie names are not very useful. Yeah, thanks.
It's a good question. So first of all, here I took some examples of movie series, but we have sports, we have live data, there are other form of data that have explicit information. But I get your question about why not use knowledge graphs. My personal opinion has been that they are hard to maintain, and the similar quality of search can be delivered by a mix of lexical and vector, semantic retrieval. Although there could be a good mix of it, where we can store certain part of this information in a graph and train some embeddings like light rag or graph lag, those things, and then have that also as a retrieval source, specifically for 2-hop queries like movies of the actor who played lawyer in Breaking Bad. Now, can this be solved with a graph? Yes. Can this be solved with just an LLM? Yes. So there are different options, but knowledge graph specifically, I feel, is hard to maintain.
I'm just thinking about the form factor of like the set-top boxes and all those kinds of things. How much does autocomplete play a factor in this? Type, because I imagine people are trying to type using those terrible on-screen keyboards and things.
Wow, that's a great question. So the median query length on Roku is pretty small. Essentially, what we do is, even if you type 1 character, we start showing the results. So we don't wait you to complete the title, or and that number is still pretty high. We want users to be doing more of exploratory searches rather than doing title searches. And to support exploratory searches, we need all this so that when a user says something, we are able to bring those results back. I didn't get your question on the form factor.
People aren't sat there with a keyboard and
Sorry?
People generally, I suppose, aren't sat there with a keyboard and on a desktop computer typing things in there.
Yeah, so that's why
they've got a remote control.
It's hard. It's very hard on the remote. That's why the query length is pretty small, and we have to support that search. People are using mobile phones a lot as well to type in and they don't even look at the screen. They just type in the whole thing. But yeah, we feel that the future is voice search and more of people being able to express themselves what they want and bring back the results.
Any other questions? Fantastic. Please. Thank you very much. Kapil.